Now let's go ahead and calculate the total flux through the ring. If I look at integral values, I can calculate the magnetic flux, which is essentially 0 through the superconducting ring because it has been field cooled here. 0 field cool. Another thing that we can calculate is the screening current that's flowing inside of the ring. So if I want to calculate the screening current, I can essentially look at the tangential H field throughout the ring here. So if I look at the field strength, the tangential field is essentially proportional to the screening current that's flowing in the ring. Now we can also calculate the inductance of the superconducting ring. The inductance of the ring is given by the relationship that the applied flux is equal to the inductance times the total screening current inside of the ring. Now this is the applied flux incident on the ring. There's actually, there would be 0 magnetic flux inside of a 0 field cool ring, so we would have to calculate the applied flux with the superconductor essentially turned off or in the normal state. The total current in the ring we can get from Ampere's law that says mu naught I is the line integral of B dot dl. So let's go ahead and calculate the total current flowing in the ring, and then I can illustrate how we calculate the flux and hence the inductance. So what I need to do is to create some contour around the ring, and I will do this using my contour tool here. So I will calculate a contour here around the ring. Okay, and I want a line integral of flux density. And we have this line integral gives us negative 3.14 Tesla meters. Now if we change the direction of our contour, the sign here would change as well. So that is the integral of B dot dl. We've just calculated the integral of B dot dl. So if we want the total current, we then divide by mu naught. Mu naught 4 pi times 10 to the negative 7 Tesla meter per ampere. So dividing by mu naught would give you the total current flowing in the superconducting ring in amperes. One thing I want to illustrate is that this value is independent of the contour that we choose here. So if I look at a different contour, I'm going to clear the last contour. I'll create a new contour, and I'm going to make a circular arc. So here I start off with a half arc, 180 degrees, and I'm going to choose a contour here, a circular contour, and look at the line integral of flux density, and I get pretty nearly the same value, negative 3.146 Tesla meters. Now that we can calculate the total screening current in our superconductor, in order to calculate the inductance, we need the applied flux. So what I'm going to do is I'm going to turn the superconductor off. I'm just simply going to not specify any boundary condition on this ring, and I solve the problem once again. And you can see that here we will calculate the total flux inside of the ring. and I obtain negative 2.26 Webers. So this would be the total flux that's incident on the entire superconducting ring. I can then calculate my inductance, simply divide the total current, and I have L in Henries. We're using SI units here.